because it has finite number of modes or steps. I think that is in any practical system you think and you are trying to model, you can, those are the features we are trying to make deterministic, and we divide them in different modes, and those modes we try to model. Like you remember in elevator control, we have defined two main modes. One is normal mode, another is when fire control is on, then the system is moving to fire mode. This way, whatever specification is given, steps in the specifications is given, are given. So in those specifications, we can divide in some finite number of modes. So one for each state of FSM, and when it is in a mode, it has a dynamics specified by the state refinement. So here today we will discuss how with this word state refinements, how we can actually use our existing FSM that we have seen suitable for discrete dynamics, how that the similar type of concept can be used for continuous and discrete both. So what will happen? What we expect when we are thinking FSM to work for continuous dynamics also? That means we have to represent our FSM in form of some actor model, where in general actor models, whatever we have seen, the gain actors, we have seen the integrators, there we have seen we have some inputs and some outputs, and those are working on the continuous dynamics. Here the difference is that we have these type of FSM where some states are defined, state transition conditions are defined through guards, and some action we have defined on the basis of this guard. So this is our main concept of FSM. But if I try to move this FSM, my concept to this actor model, my question will be how I will actually use these inputs and outputs, and how I will use them to realize my states, realize my guards, and realize my actions. For that, we can consider some number of input as well as output ports. Now, when we talked about normal actor models there, like integrator, like again, there we have thought of that these input ports will be only used as general inputs. But here, the difference is these input ports, some of them can also be used to handle my guard or this transition conditions. So it is not that all these input ports will be used for my final input, my absolute inputs. Some will be used for handling these guards. So these guards, these transition conditions, some inputs related to my transition conditions, that I will consider through my input port. Similarly, based on this regards, when some action output I have to realize, sometimes that will be my intermediate variable, sometimes I will be realizing through my output port. So basically, I am realizing these guards and actions through my inputs and outputs. And then this functionality, I am just defining as an expression inside this intermediate actor model. So this way, I'm trying to map my FSM to the actor model. Now, the question is, how can I modify these inputs and outputs? So for that, it is required to understand this state refinement or setting of action. Now, before that, we will discuss that through one example. See, we are going back here again to our thermostat model. Okay, you remember we have defined these two states, cooling and heating, the same thing. cooling and heating, and we have defined there some conditions based on the transition will take place from heating to cooling, or the reverse, from cooling to heating. But the difference here is, at that example, we have considered this temperature input as a discrete input. But here we are considering this temperature input as a continuous input. But when we are considering this GERD or transition condition, we are actually setting up a value, particular value at a particular instance of time. If it is a continuous in terms of time, or something else in terms of continuous can be. But so we are considering some temperature at a particular time t, and based on that, if that is greater than or equal to 22 or whatever that is my specification, I'm setting my actions, I'm setting my transitions. So this way, when I'm thinking about realizing FSM for continuous dynamics, I am specifying, I am considering some temperature or any value at a particular time instance t. And in that way, we are trying to handle this continuous dynamics with our FSM. So this is basically state refinement, or sometimes you can tell when associated additional variables. If you are actually talking about extended FSMs, there you have to also handle not only the state variables, but also added variables that you have defined. So there also you can optionally specify some set actions. That means you optionally consider set some value or consider some value at a particular instance of continuous dynamics, and then you can consider, you can decide your transition conditions. That means here I can see each of my states are not separate. Now this is not exactly discrete. This is basically some time-based system. Okay, and based on that, when I'm specifying this GERD, I'm specifying some value at a particular time instance t, and based on that, I'm doing the output set action. Output set action means if I am actually considered any extended FSM, there I have considered some extended variable, certain variable, and the variable value of that variable I am setting at a particular time instant, according to my GERD, at a particular time instance, and that is called output set action. So setting action and this whole state refinement is the way by which I'm trying to realize my continuous dynamics with my existing. I'm trying to combine the concept of continuous dynamics in my existing concept of FSM. Okay. So now we will discuss a very typical hybrid system when we use the timer. Okay. The timer, that is what do we say? Time when we are considering in this form, in a continuous form. But when we are designing my timer, what is the requirement? Timer means it will generate to your main system or main module. It will give some interrupt. It will give some timer input. What is that? Maybe that timer input is tick. That is your timer input. That means you are, according to your specification, you can set at which interval that tick will get generated, and that is your t. So at initial stage, you are setting st is equal to 0. That means you are starting from 0, and after time lapse t, you are generating an interrupt or a signal. You can say at this point a signal t that you can use as to your subsequent systems. So here you see, you are basically, the time is something related to continuous dynamics. But this realizing timer in this way, you can actually combining this continuous dynamics maybe to some discrete dynamics related FSM. Okay, we will come to our another existing example, but before that, for this timer, it is starting from 0. It is changing. This is the change rate of change of rate of change of the timer value. So this is how you are changing. So you're moving 0, 1, 2, and this way you are moving up to t. If now st greater than equal to t, then you are generating this tick, and this tick is getting used to your next level FSM. Now see here how we are using, we are combining this timer input with our existing example.
Ma'am.
Hello. Yes.
Like in the previous slide, like what exactly is the tick? Like I'm getting to get that.
Pardon?
Tick uh, at like st is greater than equals to capital T.
ST is your time input. Yes, it is a continuous signal. Yes, and tick.
Okay. And ma'am, tick, ma'am, what is tick?
Oh,
Like
tick.
representing?
Tick is the timer output. Like, see, what is the functionality of a timer? When you use a timer in your system or in your circuit, what do you want? You want that this timer will maybe after 15 seconds, you have sent, it will generate a signal to your and give some input. I'm not talking about signal, forget it. This timer will give some input to your main module or main system, main process, whatever it may be. It will give some indication that okay, this 15 seconds or 15 minutes, whatever value you have set in your timer, that is over. Then you can, based on your algorithm, you can move to your next step. So that indication, that input is the tick.
In this, the capital T is fixed value then. Okay, it's not changing.
This capital T may be 15 seconds, 15 minutes, whatever you have said. I mean, after which time this timer will produce some input, produce some output that will act as an input to your next subsequent module or your attached module or your main module. Okay, so this is, so when I'm telling, okay, my timer will give some input to me after 15 seconds, then this t is the 15. Sorry. Okay. This t is the 15, and this tick is the output of this timer that is going as an input to the next module. This is the rate of This is the rate of change of time. What happened? Oh, sorry. Wait. Pain is disturbing maybe. 1 second. Okay, now is it clear?
Yes, ma'am. And ma'am, okay. The representation of the timer here, s dot t is equals to 1. Like, what is this representing? Like,
s dot t is equal to means 1. What is the rate of change? Like you have said that my timer will start from, let's say, 1 minute. Okay, and it will in every step it will change the with, let's say, 2 minutes, and it will count up to 30 minutes. In that scenario, your ST will be 1. That is your initial value. Your rate of change will be 2. It is counting in the gap of 2 skip. Okay, and your final value, your ST, this action will be ST greater than is equal to maybe 30. After that, when this condition is getting satisfied, you will generate a tick. So this is the rate of change.
Okay.
Okay, rate of change. And it is changing following this rate of change. And every time when this condition is not getting satisfied, this is like a self loop. It is again changing, it is coming back to this step and again changing and changing up to this. It is checking this condition is getting satisfied. When it is getting satisfied, this tick is generated. So that is the idea of time module. So we will again go back to our previous example, again the thermostat, and we will see how we are actually combining this time oximeter in this thermostat example. Now see, remember this is related to our temperature, and this part is related to our time requirement, time signal, continuous time signal. Now we are modifying our thermostat specification a bit. Remember, there we have introduced hysteresis. We have introduced some lag where in our previous design, let's go back. Here we have discussed that we were considering the range between 18 to 21, right? When the temperature is greater than equal to 21, then only we will consider the transition from heating to cooling, or if the temperature is less than equal to 18, then we will consider the transition from cooling to heating. That means if the transition is changing from 20 to 90, nothing will happen. 20 to 21, nothing will happen. Only the transitions will take place in this 20 to 18, etc. That means we have considered a typical range to avoid what we call that, to avoid something that is called shattering. Do you remember that?
Yes, ma'am.
Yeah. So we use this lag to avoid shattering in our design. Here, using this timer, we are changing our modification a bit. We are changing, no, I'm keeping my threshold temperature as 20. That is according to my exact specification, see? But here what we are introducing one added condition, that is we will check this. For each heating state, we will check if the temperature is greater than equal to 20, and this is and condition, see? If the thermostat has remained in this heating state, or the same thing for cooling state, heating state for at least some amount of time, that is TH. So that way we are ensuring, in spite of the fact that the temperature has been changed to maybe 19 to 20, or it came to from 21 to 20, whatever may be the case, just by immediate change of 20, we will not change the state. We will change the state only if the temperature is changed to 20 as greater than, lesser than, whatever may be based on our specification. But the thermostat maintain its existing state at least some amount of time. For heating state, we have defined this TH. For cooling state, see here the same thing. We have defined this TH. So in this state, cooling state also, the thermostat will remain at least this TC time, and also associated condition is that, of course, that is the main condition of thermostat, that this temperature at that instance of time will be less than equal to 20. If that both the conditions are satisfied, then only we will change our state from cooling to heating or heating to cooling. That means we are associating here the concept of timer with my existing threshold condition of temperature checking. And maybe if we are starting from this cooling state, you can see here, if I'm starting from my cooling state, I'm setting this AST value as it is. So with the assumption that this is my time is already elapsed, or I am here at least at this cooling state, and from there my initial transition is taking place. According to your design, your assumption, you may change this value. I may change this value to, okay, I will set this as 0, and then I will check this condition. I will start my timer from here, and the timer will change. See, this timer change is also defined in this state also, inside this cooling state and inside this heating state. Rate of change of timer is same for both the states. because we are thinking about the same timer we are using for both the states. Only this HT, that is if heating is 1 or not. So this is in heating state, it is 1, it is 0. That's all. Other than that, we are combining these continuous dynamics with our existing thermostat solution. Okay, so that way we are avoiding the range. Any question?
Yes, ma'am.
Yeah.
Ma'am, in this case, like the timer, we are linking it with like if we are using it to for the heating, like for TH time, as the temperature increases more than 20, then the machine will stop, like it will stop heating or it will stop working for the certain TH time. Is it working like that?
Yeah, the specification in this case is like that your thermostat, the state in which thermostat is, if it is a heating state, then we have to check whether the temperature has been raised from greater than equal to 20 and the state, the thermostat has been maintained the state of at least greater than equal to TH sometime. Maybe you are deciding it will be 50 seconds, 50 minutes, whatever it may be. 2 minutes, 3 minutes, whatever it may be. At least that state, heating or cooling state, has been maintained for that 2 minutes, 3 minutes. Based on that, you have set TH and TC, and the temperature is also raised to 20. So both the conditions need to be satisfied.
And like as soon as both the conditions are met, the process will repeat itself. That is happening.
Yes, of course. When both the conditions have been met, then this heating to cooling transition will take place. Then again, when that is in the cooling state, then if both the conditions has been met, see, this is an AND condition. So it is less than equal to 20, greater than equal to TC. Both the conditions are met, then only the cooling to heating transition will take place. And every time when you are making this transition, you are setting this timer as 0, because when it is going to the next state, it is again checking its rate of change, and it is again increasing, and for that state it is again checking for its respective threshold. Okay,
shouldn't be there a slash before that ST equals to 0? Like we use a slash for the change.
Yeah, there should be actually that is an action, so it should be a slash, but it's just they have written the next line and that way. Okay, so this is the guard, this is the action. You're right, there should be a slash. Okay, so next we are going to this part, that is this time automation variation of traffic light control. So remember when we discussed about this traffic light controller, we have talked about these red, green, pending, yellow states, the same thing. But here you have used one counter. So we have considered that there will be a counter. The count will count up to a specific count, and we will check whether that condition has been met. Then only the next level signal will be, will be set high, and the transition will take place. So here we are doing the same thing. We can do the same thing just by using one timer, where at each state we are defining, see, we are defining here, here, the rate of change of timer. It's the same for this case, considering we are using the rate of change of timer in the same as the timer is same for my main system, and based on that we are increasing up to 60. Here we are increasing up to 5, and that way the transition is making. We are making this transition. Sorry. So this is the basic condition. Use of timer automator, time automator, what we are using in our existing FSM design. And we are basically, the interesting part is that you can consider this as a hybrid system, because you are actually combining both continuous and discrete dynamics here. Actually, this is typical example here only, because in case of if you consider this thermostat, there we consider this temperature and time both are as continuous dynamics. But for this pedestrian, sorry, traffic light related example, here you can see all other conditions, transition conditions or guards and actions, all are discrete. Only we are considering this time automator, these we are combining with this discrete events, and we are making this system hybrid. And this is one example how we are handling or how we are modeling our hybrid system. This is general for any embedded system, because there we have the requirement that we perform the state action, we perform the state refinement of my continuous signals, okay, based states, and then we model our hybrid system. Okay, so this is one concept that we just discussed. Then we will continue with our ongoing discussion about hierarchy and concurrency. Okay, let me share that slide. So now, one second, just a second. Okay. So here we will see, now I hope you remember about that hierarchy and concurrency, whatever we have discussed. So we will now see a few more compositions when we will consider our system. Maybe now this system can be hybrid system. Now you know how you can incorporate the hybrid dynamics in this FSM. So you can think these blocks maybe hybrid blocks, maybe discrete or handling only discrete events, or maybe handling only continuous events. But what can be the composition? So remember, when we have discussed about hierarchy and concurrency, we talked about that either the basic idea is that either we are grouping two components, two blocks into one block, or we are decomposing one block to multiple blocks. That means you can think both the way. You can think while we are actually okay. Wait. You can think that either I am just combining these A and B, these two components, and I'm forming one set, that is C, or other way around. I'm decomposing this C to A and B. So in both the cases, we have to understand how we will be mapping for the states and the state transition conditions and input outputs when I'm moving from AB to C, or I'm moving from C to AB. Okay. So here we are starting our discussion with this synchronous side-by-side composition. Side-by-side means this way. Okay. So where two actors are disjoint. Okay. If another important note is that when we are considering these two disjoint FSMs, that means whatever output from based on this input I1, A is generating to this O1, those are not getting affected by I2 and O2. Okay. And another thing is that if we are considering any extended variable in this A or B, so those are also disjoint. Okay. So take this example. Let's say this is your A, where you are having two states, S1 and S2. There are some transition conditions, S1 to true and S2 to true, and some action A is set. Similarly, this is your FSM for B, and you are generating some output A and B. Okay, discrete outputs. So a few terms here. If the two-state machines A and B are deterministic, then the synchronous side-by-side composition is also deterministic. I think that is obvious. You can understand. So this in this side-by-side composition, if in any state you are actually allowing some non-determinism by in some way some non-deterministic behavior is getting incorporated, of course some of your outputs will not be deterministic. So that way to maintain the determinism of your system, to make your composition deterministic, of course you have to think how you can make your components also deterministic. And this is called component-based property. That means a property is compositional if a property held by the components is also the property of the composition. That means when we are talking about determinism, that is this determinism is the property of the components of this side-by-side synchronous FSM. That's why this is called this is actually compositional property. Now see, when we are we know what are my states in A or B. Then how I can map this, or how I can understand that what will be my states and state transition conditions when I am just grouping them, or maybe the other way around. Let's take this one first, because in general when we go for top-down approach, what we do, we have a big component, we have a state, then we can divide them in multiple substates or subcomponents, and then we go to the lower level. Maybe in the lower level, if you break up C, you will get these components A and B. So here see, these are the states S1, S2, S3 and S4. So when I have to understand what will be the states and transition conditions in C, what I will consider, we will check this formally with some formal expressions. But before that, just understand with this example. Okay, before that, if it is synchronous reaction, of course, we are considering, synchronous side by side, we are considering A and B composition. In general, side by side, if it is asynchronous, it will be A or B. We will coming into that. So here, what will happen? First I have to decide what will be my states in C based on my states in A and B. So we will just take the ordered pairs, okay, or pairs of the states. So pairs means we will consider one state from A and one state from B. So that way, what will be my possible states? One possible pairing arrangement can be S1, S3 and S1, S4. So that one, S1, S3 and S2, S4. See, this is my first arrangement. Okay. In second arrangement, what pairs can I make? Another pair is S1, S4 and S2, S3. So that is another possible pair. So based on this S1, S4, this is my one step, can be my one step of C, and S2, S3, that will be my another state. Now go back to the first one. Okay. When I have considered my sets in this way, S1, S3 and S2, S4, what will be my possible transition conditions? See, when I am moving from S1 to S1, S3 to S2, S4. First, I have to check S1 to S2. What is my condition? I have just one set guard that is true, but no action specified here, right? So that means here I have to consider, and also I have to consider the transition condition for S3 to S4 for this pair. So S3 to S4 is true. Along with that, my another added action is B. So finally, this is true, and this is B. So this is my state transition condition when I'm considering C and when I'm considering S1, S3 and S2, S4. Okay. Similarly, if I consider S2, S4 to S1, S3, just check S2, S4, S2 to, that means S2 to S1, right? S2 to S1 is true/A. This is the guard, this is the action. And another possibility is S4 to S3. So both I have to consider. S4 to S3 means this is only true given. So that means when I'm considering these transition conditions, I'm just considering, I'm clubbing these to all these reactions and guards, all these guards and actions, and I'm getting this final transition condition or my guard and action pair. Clear? Similarly, check this one. This is here I'm considering the pair as S1, S4 and S2, S3. So here I have to consider what are the possible transitions. Here my possible transition again S1 to S2, S1 to S2 again true to, and S4 to S3. S4 to S3 means here see true, but there no action specified. So in that case, S1 to S4 to S2 to S3 transition, my only, I mean, what to say, my only guard is true, but there is no action, because in both the cases, there is no action specified. This and this. Okay. This is basically getting mapped to this one. This one. Similarly, for S2 to S3, when I'm moving to S1 to S4, see what is there? S2 to S3. See here. Sorry, S2 to S1, true/A. S3 to S4, or yeah, S3 to S4, true/B. So basically this one and then this one, both are getting mapped. Okay. So, and this is my transition condition. So this is the S2, S3 to S1, S4. When I'm considering this, see, I'm considering true as my guard from both the cases, and A and B, both actions will be considered. So this way, when we are making this, when we are clubbing these states together, we can say when we are fusing these two subcomponents and we are making one state, we are mapping to one state. What we have to identify? First, we have to identify the states, and then we have to identify the transition conditions. Okay.
Ma'am?
Yes.
Ma'am, in this there would be some states, for example, S1, S3 to S2, S3 would also be a possible transition, as when S1 changes to S2, but S3 remains the
Can you
same.
repeat once again? What is with the state you are mentioning? Can you
Ma'am,
repeat?
on the left side, it may
Hmm.
be possible that S1 changes to S2, but S3 remains the same.
Actually, how we define it, we take generally the pairs. Pairs means I will come to the actually formal definition of it. How we form those states. We just pick one state from here and pick one state from here. Then we make the pair. And again, we pick one state from here and we pick one state from here. I mean, we pick once, maybe you can think in this way. We pick one state from here and first we can identify what are the all possible, what to say, what are the all possible pairs. So these are the all possible pairs, S1, S3, S1, S4. Then we make the transitions to other possible pairs of states. Okay, so what you are telling that S1 is remaining the same. Okay.
Yes, ma'am. For example, ma'am, we have two machines, two FSMs, A and B. So, ma'am, it might be possible that B does not change its state, but A changes its state. So that we have not taken into consideration in C.
B doesn't changes its state. That means B is a one single state. You are
Uh,
telling, if you are telling B is no, that is fine. Where your confusion is, B is not changing its state. That means whatever you are considering, this B it is not considered. It is not required to consider that one FSM, right? That is one single state, right? Maybe you can consider that is B.
Ma'am.
Is that the thing?
uh, uh, no, ma'am. For example, if I remain in S3 and there is no B, then my state B would not change because S3 would not transition to S4 unless there is B.
Yes,
So all
unless there is B. So when we are actually, you are trying to, consider at a specific instance, right? And you are once you are telling unless there is B, or unless so there is some condition is getting satisfied, that means we are considering that a specific instance or specific condition. But here when we are considering, we are mapping these EB components to C, we are actually considering all possible options, right? So if you are telling that there is no state transition, that means it isn't that not enough. Is it not enough that we can consider that one single step? Or if I'm just if you are thinking that okay, that state will not change on the basis of B, right? So in that case, we will not be considering B, okay, but we have to consider the other transition conditions.
yes, ma'am.
Am I getting your point, or is there any more doubt?
Ma'am, I'll probably spend some time later on this. Then I'll probably
Okay.
understand.
Maybe you can come up with an example that will help to all of us to understand. Maybe you can come up with an example what you are actually trying to say, and we will check it out. Is it that okay?
I also got confused a little, ma'am. Ma'am, you may continue. I'll look into it, and then in the next class I would probably ask.
Yeah, that will be better. And you just come up with maybe with an example or something like that. That what are you meaning by maybe a single set? Because single set means something different. And if you are telling okay, some condition is not getting satisfied, or transition condition is not getting satisfied, that means maybe some instance when it is not getting satisfied. But that doesn't mean it will not get satisfied later. So which one you are talking about, just come up.
Yes, ma'am.
Okay, sure.
Ma'am.
Yeah.
I have a similar doubt. Ma'am, if you consider the right side table, so there is like 4 pairs, right? S1, S3, S2, S4. But transition is between only 2 pairs. So, is it not possible from the S1, S3 to S2, S3, one state from the top to the one state in the bottom? Some transition is it not possible?
I'm not getting. Can you come up one thing? What I will do? Let's say you are suggesting me to design C in some other way, right?
Yeah, S1, S3 is there, and S2, S4. Like there are transition between those two, right, on the top.
Yes.
But is it not possible, like a transition from S1, S3 to S2, S3 state?
S1, S3 to S2, S3.
Yeah, in the bottom there is no transition currently shown like that. Is it not
No,
possible?
because according to this specification, whatever is there in your in your given subcomponents, that transition is not required, because in your given subcomponents you have only considered S1 and S2 states in A, and in your subcomponent B you have considered S3 and S4. So when you are merging them, the rule is, or the way you have to do, you have to consider all possible effects. How can you consider the all possible effects? You have to consider one set from one subcomponent, and then you can pair them up with all possibilities from the other component. Okay, that way we are doing. We are picking this S1 from A, and then we are pairing them with S1 S3 and S1, S4. Now we are checking the transition with the other part. Like now we are considering S2, and then we are making S2, S3 pair and S2, S4 pair. Then we are making the possible transitions. So can you come up with an example if that is actually required? According to this subcomponent, that is not required. But if some S2 state may be a part of this A also and maybe a part of this B also. In that way, maybe that transition would have been required. Okay, if you are thinking about, we will come up with this. I mean, some shared states and all, shared variables, all these things. Okay, maybe that time these component, I mean, merging will not be so simple. Okay. Let me continue. I will come up. Maybe you can come up with some example also, then we can discuss. Okay.
Yeah, ma'am. I will look up and come in the next class.
Yeah, sure. That will. Okay. So this is how, this is formal definition. Wait. Hello? You can see the screen, right?
Yes.
Okay. In this synchronous FSM, now how, actually this is a formal definition that we have just explained with some example. This is a formal definition by which we will decide what will be my final output and what will be, I mean, my final inputs. See, these are my subcomponents, this A and B. Here you can see these are the states of A, inputs of A, outputs of A, update function that is acting upon the states and input to generate this output, and some initial state defined by the FSM of A. Similarly, this is the states of B, inputs of B, outputs of B, and you understand the meaning of update. Update condition means the same as transition condition or your guard. That is that you are actually that is acting on the state and inputs, and that is generating the outputs. Okay, and the initial states of B, that is defined. Then the synchronous side-by-side composition will be given as, see, this is the pairing of states. You can see by this symbol. That means you are that whatever we have seen in the example, you are picking a state from state A and you are picking a state from state B. And then you are making the pairs, you are forming the pairs. So your state C will be all possible such pairs. Similarly, for inputs, you are making the pairs for inputs A, inputs B, same for outputs A, outputs B. Initial conditions, you have to consider all the initial conditions. It is not about pairing, because for proper modeling of your FSM, you have to consider the all proper initial conditions. Then what will be your final update condition? C. Then you are applying this update of C. Now, these are the AC is B. Basically, these are the states. One state is taken from your state A and one state is taken from your state B. And these are the inputs. When you are applying this update condition, update condition means your guard or your transition condition, whatever you can tell. You are basically generating these states. I mean, what to say? These are the modified states of your. Yeah, these are the. Wait, 1 second. Yes, these are the modified states of your. You can see how we are defining this is dash state. That is when you are applying update or your guard on your inputs and your states of A. In your states of FSMA, you are getting these states is dash state and your output of A. Similarly, when you are applying this update function or transition condition on the states of B and your inputs of B, you are basically getting these modified states, and this is your outputs from B. So these two are basically equivalent. Okay, this is for synchronous FSM. And for all states, you can understand this is already defined. So just go through it once. I think it will clear your doubts about the previous example. Why we are actually considering the pair, because this is by this definition, you have to choose one states from each of the subcomponent state machines, and then you can form the state set of your final, your superset, or your what we can say main component. So that way we are forming the states, we are forming the inputs, we are forming the outputs, initial states to understand. Then this is the update function that is acting on the respective subcomponents, their states and their inputs, and that is basically generating the final states and the outputs. Okay, so this is the basic definition and basically how we are defining our final states when we are clubbing the both. Okay, is it clear?
Yeah.
Okay, so this is the idea of synchronous FSM. Now we will go to the asynchronous part. Asynchronous part means what? Synchronous means A and B both are running. Here the asynchronous means the A or B. Okay. So in this case, the choice is non-deterministic. I think probably that is what you were telling. I'm not sure, but you come up with your examples.
Yes, ma'am.
This is
Yes, ma'am.
Yeah, this one you were telling, right? So this is, remember initially we are talking, this one was for synchronous, when both are running. So that time we are considering these specific states. But when you are considering A or B, that means the choice is deterministic, then any type of these transitions are also possible. Maybe you were mentioning about these transitions. Okay. At this stage, what is the difference? See there. Wait. See this now. Here this update condition a bit different. Here is a relation between either or. Okay, that means here the state formation is almost similar, but here you are considering S1, S3, S2, S3, S1, S4, S2, S4, all these things. But when you are considering the update condition, see here, you are applying this update on the states of A and B and on the inputs of A and B. And what you are generating, the modified states SA dash, SB dash, and this modified outputs. And here, this is very important, this either or part. Here, when you are applying this update function on this SA and IA, you are getting this SA dash and OA dash. And SB dash can be OSB, that is your existing state from you have taken from SB, and your output B can be absent. Okay, this modified output can be absent. Or what happens, you can be updating, and here you are just considering your update function on this states of B and inputs on B, and then you are getting this. And your SA dash will be EC, and this output may be absent. So maybe either or is working. That means when you are considering this final output, OA dash or OB dash, one of them may be absent, and your final output may be given by only one single subcomponent. Okay, that's why a reaction of C is a reaction of one of A or B where the choice is non-deterministic. This is anything may happen. So this is for the when we are talking about asynchronous side-by-side composition. And we will take one example and we will see on one. Okay, so see here again we are back to that same components A and B. But here when we are merging, we are considering S1, S3, S1, S4, S2, S3, S2, S4, and then these transitions are also present. Along with this, these transitions are also present. Okay. So let's take one example. This is an example of asynchronous composition. Asynchronous means what? Either A is working out, giving you output, or B is giving you output. Okay. So, I mean, your output is getting affected from either your component A or it is coming from B. Okay. So let's consider this example here. Consider two servers that can receive requests from network. Okay. Each request requires an unknown amount of time to service. So the servers share a queue of requests. Okay. So there is a queue. There are two servers. This is the server 1 and this is the server 2. They are taking requests from your network. Now there is a concept of pending queue. Okay, so the servers share a queue of requests. Maybe you can consider that a pending queue. Pending queue means whenever some request is coming, it is not never happens that the server, it may happen that server is busy at that time and your request cannot be handled exactly at that moment. So it will get stored in that pending queue. So these two servers, they are running maybe in parallel, but whenever any server is checking and any task is there in the pending queue and the server, any server, maybe server 2 is now free, it has completed to serve its request, then it can take another next request from the pending queue and it can process. So maybe the request is coming for this server 1. But that doesn't mean that the server 1 only can process that request or serve that request. Maybe if it is going to pending queue, server 2 also can process it. So this one you can model with this is the step machine modeling of that your specification. Let's see what is going on. Maybe some request is coming. Okay. That request, you remember we have talked about some shared variable. You can now consider that request may be somehow stored in some shared form. Okay. And that request going to this part and this also. Maybe for the sake of simplicity or to match with our specification, we can think initially this request is going to server 1. But at that time, we have to check what is the state of the server. Okay. Now let's take what are the states of the server. The server can be idle or server can be serving. These are the two states possible. Okay. I think this is better view. I think this is the same. This is the just I want to tell that the states and the state transitions are same for both the servers. So I'm just showing that here. Maybe you can see it clearly. So when a request is coming to a server 1, you can check what is the state of the server. If it is in idle state. So there are two states we are considering, idle and serving. Okay. So when some request is coming, and that request, if it is in the idle state, server is going to the serving step and it is serving. Maybe that is for the first request. Next, if the second request is coming, then what it may happen, this server is in serving state At that time, what will happen? See if the request is coming. Okay, first for the first request, server went from idle to serving this transition, and by serving this request by this action, it is completed that request, and this set this done variable high. Done output high. So this done is going to done A, and it is showing that server has completed the first request or some request at a time instance T. Next, when another request is coming, if this request it is a request input high, that is request guard is set, and the server is in this serving state. At that time, what will happen? This pending will be increased to pending plus 1. That means that task will be added to the pending queue. Okay. Now, this is another reaction. Now, there is no request, not request, and pending greater than 0. So, what will be the action from the server's part? That server will take one task from the pending queue, and then it will continue its serving state. Okay, that's why there is a decrease in the task in the pending state. So pending is equal to pending minus 1. Okay. There is no request, and server has not any request. It has taken from the pending state. It is completed the serving part, and this from this serving part, now it will check if it is there is no new request and the pending is equal to 0. Then it will set the done, and done will be given to. So these are the few transitions possible. So is it clear, right? Hello?
Yeah. This one state, like when there is no request and there is no action, what is the use of that part?
When there is no request.
Top one.
The top one, no request, means it is again entering the serving part just to check once whether there is any pending part or not. That's why for this one, this one after checking, it is checking that no request and pending is equal to 0. Both are true or not. Then only it is moving to idle.
Ma'am, but is it required to use this? Like, because anyhow we are checking that.
You can tell that together you are checking, so you can move it here. Maybe initially, you can actually avoid that part separately. When you are checking this one, you can actually avoid this part, separately checking it. If there was no concept of pending queue, maybe that time we have to check whether any more requests or not. And if not, this time, this one we can actually remove. And there is no request and pending is equal to 0. Of course, it will move to idle. Okay. Yeah. So this is the same thing for server 1 as well as server 2. The same thing. Only thing is that this done A or done B, this done output, when it is coming, sometimes it is coming from maybe server 1 and maybe sometimes it is coming from server 2. So that is side-by-side composition, but they are asynchronous. They're working in either or mode. So this is one example of your asynchronous side-by-side composition. Okay. So now this one we have already discussed. We will actually discuss more on it. This one I want to just mention one thing. See, shared variable we have talked about. Okay, we have seen here that these requests can be a shared variable. This is shared variable that can check what is the status of your shared, and also this pending queue. Those will be some shared variable or some shared memory locations, because whenever you are storing the pending task, those details, that will not be just any variable, single variable. That may be some memory locations from where you have to fetch the task details to perform in the server. So this is not about when you are talking about this type of shading. It is not always about the only a single variable, but also how you are storing some few details. So for that reason, this part we will come again when we will be talking about actual design. See, in this case, for modeling purpose, we are just considering, okay, we know this is shared variable, we are storing somewhere and we are fetching for this. For embedded software design, that is not enough. Remember in our introductory class, maybe we have talked about that. When we are talking about embedded software, we are just arranging some instructions, we are doing the modeling. But it is not that all, because when you have to improve the performance, or you have to, what to say, improve your software design, you have to also know how your environment or how your play, what is the, you should have some knowledge about your environment, about your platform also. This is one example. When you are storing this shared variable or these shared information, maybe it is when you are and you are designing your software, it is important to know what is your memory storage, typically where you are storing this, what is your memory access levels, in which way, whether you are using directly from your main memory, or are you using some intermediate solutions, what is your memory structure model. Next one is what is your memory consistency model, and how you are handling your atomic operations. Like, it is difficult if you are using, let's say you go back to this request or pending variables. When one server is accessing that, maybe one server is running, maybe accessing, at the same time, if the server 2 is also accessing that shared variable, then it may happen there is some discrepancy in what value they are reading. That mostly happens when we when we try to read, let's say maybe there is one variable when this server is writing, server 1 is writing and the server 2 is reading. Now it may happen if both are doing at the same time, then whenever the server 2 is reading, it should ensure that it is reading the absolute current value. So that way, how we will ensure that your atomic operations actually working correctly when you are in a shared environment. So for these details we will actually discuss not in this modeling part. When we will move toward design part, implementation part, that time we will come up with this in detail. But now, as of now, you understand that here when you are actually designing this type of maybe asynchronous, whatever may be your scenario, you have to take care of your shared variables. Okay. Next, yeah.
Ma'am, can you go back to the previous slide? Yes, ma'am.
Yes.
In this case, in the serving part, when there is a request, we are increasing the pending value, like decreasing the pending value. Okay.
Not always. When there is a request, not always. Actually, this request, it is directly it is going to done. If the server is in serving state, maybe some more guards of course need to be added in this part. Server is the serving state, then that request is actually increasing this pending is equal to pending plus 1.
Ma'am, because these two guards are like at the same time.
You are correct. Actually, there should be some more details. Just this is a basic thing. Transition conditions have been added, but there should be some more. That is, request is on and server is in a serving state. For some time maybe there should be a time check, or server is there maybe some additional variable that will show that server is at this moment is not ready to take another request. So that part should be added. Otherwise, you are right. This will lead to some non-determinism because the same state, same transition conditions. Of course, that may lead to some non-determinism. There is a possibility, but this is just basic idea it is giving, that if this request is on and then it is set high, then two possibilities: it may go to the done state, it may go to pending plus n. Of course, there should be other variable that will show that whether server is willing to take or in a state to take another possible request, maybe within near future or not. So those things should be incorporated in this transition. Okay.
Yes, ma'am.
So, but this is just giving the idea of asynchronous your side-by-side composition, that either of the servers are working, and when it is setting the done part, it is set by either of them. Okay. So that was about side-by-side. Now we will move to our serial composition, when A and B, these components are arranged in this way, side by side. You can see this is one state machine of A, this is state machine of B, and this one, it is this, this, when it is setting this B high, B action variable, this B action is basically acting as an input to the next FSM. So this is serial composition. So in the simplest form, cascade composition or serial composition, whatever you say, implies an ordering of the reactions. So one FSM is generating some reaction, and that reaction is basically acting as a input transition or in the next level. So again here, you are having the same question. Whenever you are having these type of transitions, how you can merge those states and how you can merge those state transitions. Typically, the idea is very similar. You have to again consider the ordered pairs. See, you are taking this S1, S3 and S2, S4, or S1, S4 here and S2, S3. Again, you are taking S1, S3 to S2, S4 transition. For that, see, S1, S3 to S2, S4. First, I will check S1 to S2 transition. So this is the transition condition, minus A. This is coming here. And from S3 to S4 transition, let's take S3 to S4 transition. This is, one thing. This one is just for when you are actually a little bit different. See, this, when you are merging this A and B and you are taking this component C, this B, this is like your intermediate variable or intermediate transition condition. Sorry, intermediate intermediate active action value that is acting as the input of your next level. But when you are fusing the state, we are basically not showing in our final state, we are not showing the effects of this intermediate value. Okay, so if you see, when I am moving to S1 to S1 to S2, yes, minus A, that effect we are showing because it is at the output. It is the absolute input coming from your environment. Then that transition condition we are considering. Then S2 to S4, S3 to S4. If you see here, the transition condition is minus B, but that is some intermediate value that is generating due to this action GERD and as this action, and it is the intermediate value. This intermediate response we are not considering when we are just fusing these two states. Okay, rest are all same. You can see here S2 to S4. Now you see S2 to S1. This is true, and S4 to S3. This is also true. So this is the transition condition. Again, this is S1 to S4, S2 to S3. So S1 to S2 you require minus A, and S4 to S3. See, S4 to S3. This is true, so nothing else, minus A. And S2 to S3. S2 to S3. S2 to S3 means S2 to S1. Let me check. S2 to S1 is true. And S3 to S4. S3 to S4, that is again minus B. Oh yes, this is minus B. That's, since it is minus B, again we are just considering this true. This transition condition, because we are not considering this intermediate value, because in serial composition when we are breaking into it, we are going deeper, and when we are considering those subcomponents, maybe we are considering these sub values, but when we are merging them we are not considering those values. But I mean, you can think this as an advantage of when you are thinking the other way around, when you are basically coming from C to AB. Okay, that time when you are actually splitting those states, splitting these steps, then according to specification, you may decide what will be these intermediate actions, and that may give some better and deeper understanding of your design through this component approach. Okay, and there is one.
Can you show like how can we that reverse, like how will we decide whether there will be a condition like minus B or B conditions, like because there is no clue in the right hand side regarding
not here is no clue, but I will come with an example. Okay, here is no clue, but according to your specification you can see these states and the transition conditions, and when you are actually splitting the states, maybe you have merged S1, S4, S2, S3. When you are splitting them to S1, S2, S3, S4, you are focusing on these separate states, right, in your components. So at that time you can consider from your specification what will be your separate condition to make a transition from S1 to S2 or S2 to S1. Okay, maybe when we will come up with a serial composition example. Okay, maybe that in that part it will be more clear. But this B or these B type of intermediate values you can only understand when you are splitting this part. When you are not thinking S1 and S4 are fused or together, you are separating them. Now you are thinking, okay, S1 is my smaller state and S2 is my smaller state. Then you are deciding, is there the whatever input I am getting from A, is it sufficient to make a transition from S1 to S4, or is there any other intermediate condition, action, anything is required, or action or any intermediate signal? Basically the idea is whether when I'm making a transition from S1 to S2, is there any added signal I'm setting? That signal is basically acting as an input, as a transition condition to make subsequent transitions. That way we are splitting. I will come up with an example, maybe that time it will be clear. Okay, so another thing is that for these transitions, see this S1, S3, S1, S4. Here is one single transition. Can you tell me why it is there? Anyone? Why this transition here?
Because there is self loop for both.
There is a self loop, exactly. There is one self loop. From this self loop, these S1 to S1 transition is coming. Okay, so this way we are understanding the states and we are understanding these transitions. Okay, so we will see with an example. Again, we will go back to that. Yeah.
I'm in the previous slide.
Yes, this one.
Yes, ma'am.
No, this one.
Yes, ma'am.
Yeah.
Yes, ma'am. In the place of minus A, can I also write minus B?
Minus B, but is the minus? See, this minus B, you see, go to a component A. Okay, in the self loop, see when S1 in the self loop, and the transition condition or the guard is A, you can see B is your action variable. You can see B.
Yes, ma'am.
And these B you are taking as an input to your next component. I mean capital B. The small b is your input to your capital B component. Can you see that? So this input, whatever it is coming from your environment, it is not that, I mean this B is not coming from your environment. So that means when you are fusing these two states, A and B, you are clubbing, you are merging them, and you are making C. At that time, there was no concept of B. Right?
Sure.
Maybe you are take this example. Maybe you are having a state, you are in the state 1, and you are coming to state 2, and while you are in the self-loop transition, you are generating this B. And when as the B is getting generated, this B is setting a condition to the state 3, and at that time this S3 is coming to S4. Right? But when you are considering this C, it is clubbed. You have clubbed together this A and B. So there is no concept of separate states, that is S1. There is no S1, separate state. See, there is one state where you are considering S1 and S4 together.
Yes, sir.
Right? At that time, if there is no way that you can generate this B signal as a state output, if you can still generate this B as a state output, then only you can consider. But if you cannot generate this B as your some state output, some action, when we are setting this some variable action, I mean this is the concept of extended FSM, right? When we are just setting some action variable, that means that is defined as a separate variable that is not incorporated inside your state, right?
Yes, sir.
If that's so, if you can actually set that variable in that way, of course you can use that in your intermediate design. But so far you have fused them and you are not having that separately. It is fused inside your A component and B component together. That time in C, you cannot use it. You can show it. That time the gross transition is taking place from S1, S3 to S4 based on this transition A or B. Actually, you take one example. I think that rather than theory, I think with that example it will be clear. Okay. Yeah.
Just one second. Like
Yeah,
from
yeah.
S1, S4 to S1, S3,
Hmm.
like for the self, we are adding A part. But in this case, S4, there is a transition from S4 to S3 also. Shouldn't we include the true part also, ma'am? The guard part?
S1, can you come up again? S1 to S3.
From S1, S4 to S1, S3, A is coming from the self guard. But we are not considering here S4 to S3 part also, because that is also happening, right? Though
Yes.
the true
No. We are actually considering. See, true means when I'm writing this transition condition true means it is true for all conditions. Always true. This transition will always happen. So here, this transition will happen only S1, S4. There is a transition from A. So both these two states will make a transition to S1 to S3 when this transition condition A is true. And all the conditions are true. So this is other than true. Basically, true is always there. This is other than true. These A conditions should always be, that is some specific condition that need to be satisfied. That's why we are actually mentioning those specific conditions. You see, always, see, that same thing may happen S1, S4 to S2, S3. Right, here only we are writing this A minus A. But ideally, that true condition you can see is 4 to S3. Yes. This here also we are not writing true.
Yes, ma'am.
Right. So this is for this is the convention. That true means always true. True. But when we have got some specific condition, we will be mentioning them. Maybe that particular condition or maybe multiple such conditions in a and or fashion. But that time we are avoiding true. True means always. Okay. Okay. Now we will see one example. See, remember again that traffic light controller. We are going back to that example. If you remember that time when we have talked about that pedestrian related FSM, there we have thought of some, we considered or we have seen that there is some possibility of non-deterministic behavior, right? Here we are actually defining or designing a pedestrian crossing light. And according to our specification, say something like this, that we will have two states of this pedestrian crossing light. That is, one is green and one is red. Okay. Now, pedestrian count, we are starting from in this green, pedestrian count is equal to 0, and that count will increase up to 55. This is just a number we are taking according to our specification. When this condition is getting satisfied, it is greater than equal to 55, then this pedestrian red will be high, and this red will be, the transition from, it will take the transition from the crossing light, will take the transition from green to red. Mind it, this is the pedestrian crossing light. We have to merge that with our actual traffic light controller. Okay, so what is our purpose? Let me first show. See, this is our pedestrian traffic light we are talking about now, and then this is our the same traffic light controller. Now we will be merging these two. Okay, so first we are, we will discuss this, what is my specification here, what my states here, then we will check how we can merge. Now, one important part is that why it is actually cascaded composition. See, okay, first see what are the states and transition. So now I think this is green to red, and then from red to green. In this case, pedestrian crossing light will be in the red state, and when this sig R, if you remember sig R, remember we have discussed the sig R, sig G, these type of signals in our traffic light controller. That means now the red sign of the traffic light is on, right? To be on. For that we have said, you can see it here again. When the sig R is high, it is making a transition from yellow to red, and the traffic light is going to its red state. At that time, when the sig R is high, this pedestrian light will go to its green state, and basically the sig R will set the action variable, pedestrian G, and it will move to its green state. And at that time, it will again set the pedestrian count as 0. Okay, like our initial state. Again, in this green state, it will count from pedestrian count to greater than or equal to 55. 1, 2, 3, it will increase. And once again, it is up to 55. It is considering 55 pedestrians at a time, or pedestrian count at a time. Then it will move to red. So this is making why we are changing this state FSM. First of all, we are changing this because we are making it more deterministic. If you remember whatever we have discussed there, if you refer to your previous slides, there we have considered some states, that is none, one is crossing, and one is waiting. And there we have seen when we are moving from none to waiting, that lead to some non-deterministic behavior, because we have no idea that how many people will be waiting and how we will model them. So to avoid this, here we are not considering fully our environment. What we are considering, we will just set our count by our own. We will set this count like this, and after this count is over, we will actually make the transition from green to red, and that way my crossing light will control the crossing of our pedestrians. So we are not, because whenever we are directly trusting on the environment, or whenever we are trying to follow our environment, that is very difficult to model. To avoid that kind of non-determinism, we make some deterministic assumptions. Maybe this is not correct, not always correct, need to be modified, whatever it may be. But that gives my system, my modeling, some amount of determinism. Okay, so this way we are actually defining this pedestrian control.
Ma'am, P count here is timer like 55 seconds, right?
Yes, it is like a count. P count can be a 55-second, or it can be some interval where we are considering just 55. It can be anything.
Like
okay.
As soon as the timer reach 55 seconds,
or yes, you can think in that way, or as soon as it will be peak on my pressing of my that pedestrian light button will be 55. That can be the count, whatever.
But
Maybe
then the action is pedestrian red. In that way, pedestrian will stop, right? Pedestrian will not move after that.
No, pedestrian red will not allowed after that. That means, see, that state is green. Okay, the counter or the pedestrian is requesting and they are passing. Maybe they are pushing the button or whatever you told, that you are setting a counter that you will be allowing 55 seconds. When that is over, you have allowed the maximum count, or you have allowed the maximum time, whatever may be your assumption according to your specification. Then page rate will be high. High means now your pedestrian controller light will be in the red state. Okay.
Yeah, it can also be count also. Like if there is a sensor who is counting the pedestrians.
Exactly, that can be counted also. Exactly, anything is possible. Okay, that is absolutely based on your specification. That's what I'm telling. But another thing, that can be a timer also, that you are allowed 55 seconds. It can move to green. That can also happen. That maybe lead to more determinism, because sensor. How many times? What will be the delay in between? Which time this 55 pedestrians will come and on or not. So that way there are different issues. I'm not going into that. What I'm telling, based on your specification, whatever may be your assumption, this checking will be done, and then when this condition is getting satisfied, that means the pedestrian passing time is over. Crossing time is over. So that's why you are setting this pedal. It is going to the red state, and when from this red state, it is signal R. Signal R is high. It is going to the signal R means your traffic light at time for the to the cars, to the vehicles, it is showing red, right? So at that time, it will again make a transition to its green state. That means that time it will again allow the pedestrian to cross the road.
Okay.
Clear? Okay. So now in this case, we are considering this is the pedestrian. Yes, hello.
Yes, ma'am. Can you please move to previous slide?
Previous slides. Yes, previous slide.
Ma'am, synchronous cascade composition in it, like, can we say like every time whenever we have like if then condition? When if
Pardon?
this thing happens,
can you repeat your question again? Not clear the voice. Yeah.
Yes. Ma'am, in synchronous cascade composition, can we say that whenever if and then condition occur, like if this condition satisfies, then we can move to next condition. So will that thing be same as a synchronous cascade composition?
See, this is synchronous cascade I'm talking about.
Yes, ma'am. Yes, ma'am. That's what, like, our next output, our next state should be dependent upon the previous state's output, right?
Exactly. It's a synchronous cascade. That's what I'm talking about. See, you have cascaded two different FSMs. You can think in this way. That's why, let me go to the next slide. Maybe you can think about these two, this one and these two. These are cascaded, right? This seeker is basically giving this input to your pedestrian. Okay, and that is based on that input, maybe you can think, now you fuse these two. Okay, this figure, if you only see here in this final cascaded composition, we will see Siglar will be present because it is also working for other transitions. But for this intermediate transition, see, for this intermediate transition, when we fuse these states, there is no effect outside. So whenever you are modeling this what to say, this traffic light controller and pedestrian light controller, what happens, this figure acts as an intermediate input, intermediate signal that is trying to control this red to green transition, and that is coming from this yellow to green red transition. This signal is getting used for this intermediate transition. But when you model this, you are basically concerned about the states as a whole, as together. So this, then at that time, this operation becomes an intermediate operation. So that time we are not considering this cigar, signal R, this red to green transition for whatever it is getting used. But if you will see, but you will say immediately that, ma'am, here we have that, right? Signal R, we have that, we are using in different, we are mentioning this at our final FSM, because this signal R is not only for this intermediate cascading, this is also for some other transitions. So whenever you are using this for some other transitions, not a single cascading, and you are fuse that component, then you can of course mention that figure also in your final FSM. Okay.
Yes, ma'am.
So here you can see this modification. Okay, before that, what will be our states? Obviously, if I go by definition, what should be our states? How many states are possible? Red, green, or green. I mean, maybe, yeah, you can start from here. Red, red, green, red, red. I have green, red. I have pending red. I have yellow, red. I have red, green. I have. But why not green, green? Why not pending green? Why not yellow, green? See, in this modified design, it is not there. So can you tell me, is there any idea why we are not considering this?
Ma'am, it's not feasible, like when
It's
the
not.
vehicles
Exactly.
are
So these are not feasible. That's why, in spite of the ideally from the basic definition, these are the possible states, but these are, in FSM definition, we call it unreachable states always. That's why we are not considering them in our final cascaded composition. Okay, so this is the basic idea about just go through these states and the transition conditions. You can understand how these two of these conditions, all these sub conditions, we have merged and we have generated all these conditions. Okay, go step by step, sit with these two separate FSMs and check whether this FSM is okay or not, whether you think that we need to add something more or something like that. The only thing is that these few states you will not find, because you have to always check when you are actually fusing these states. By definition, you can fuse and consider all possible pairs, but when you are actually going to model, you are considering your final model, you have to actually remove those states which are not reachable. Okay, so so that is the main takeaway from this example, and just go through the states transition step by step and let me know, do you have any question, or do you think these transition conditions are okay, or we need to add something more? Now you understand, right, how from these few states and separate states, we can, the states we have already mentioned, and how we can actually consider what will be my transition conditions. So based on that idea, whatever we have discussed in our previous example, just go step by step in this example and check and let me that whether it is correct, that transition conditions are correct or not. Okay. So that is your job. And let me know if you have any doubts. We'll again take it next day. So far, whatever we have discussed, this is like this. We have considered some general composition. We have considered some side-by-side compositions. What will happen if those are synchronous? What will happen if those are asynchronous? How I will realize my final FSMs, or how if I have final skew state, how I will, main thing is that in generally when we design, we divide it separately. And when we go from bottom-up approach, we merge those states and try to develop my superset based on our requirement. So here, if this is my superset B, from there, I have these subcomponents, how to arrange them, how to realize the final FSM cycle. Then from B to A2, again, this is one type of cascade composition. So again, what will be my inputs, outputs, how I will decide the states, that we have discussed. But one thing we have not discussed, maybe we will take it next day or day after that, that see here we have one feedback. So if that feedback would have been not there, then separately cascade, separately side-by-side compositions, we know how to deal with it. But what about this feedback? So what we will, how we will handle this feedback, that we will take up next day. Okay. So one quick another discussion, maybe other modules will start next day. Hierarchical models we discussed in the previous day. The concept we have, right? We have some hierarchy, and maybe in this case we have A, and this B we have broken into C and D. So when the transition is taking place, maybe when we are entering B or we are coming out of B, we are selecting, maybe we are choosing one of the states from B, maybe it is C, maybe it is D. Okay. So that separately we have discussed. Now, this is the final fused FSM. When we consider now A, C and D separately. This is one example I think we should mention while talking about hierarchy that we have missed last day. So when we have talked about A and B, basically B is broken into these two subcomponents C and D, right? So when I'm making a transition to A to C, what will be my transition conditions? See, for A to B, to go A to B, I have to consider G2. That is my guard or transition condition. So G2 will be there. And A2 will be my action. So if in that way, I will be entering to C. My assumption here is my first initial, see here it is given that whenever I'm coming to B, according to this specification, my first state will be C. That is my initial state. Now this can be anything. This is for this example, but when we have talked about history, remember, if I am storing, according to my history, I have to come back to D, then these transition conditions will change. Okay. As of now, for this example, just consider that I am entering from A to B, and for B, it is defined in such a way that C is my first state. Okay, initial state. So I have to practically come to A to C, and then I can move to C to D. Okay, but so that way I'm defining this transition conditions A to C and then C to D. Then I can come back to D to C, C to A, everything is possible. Here see, When I'm coming out, okay, when I'm coming out, there is two possibilities. I mean, I can come out from C and I can come out from D also. Okay. So based on that, I am just considering the transition conditions. I'm just showing how I'm actually realizing the transition conditions, what will happen. So A to C, it is very straightforward. Whenever these guard and will be satisfied, G2 is getting satisfied, I'm entering to C. And then the action will be taken place. This A2 variable will be set, or this A2 action will be taken place. When I'm coming out from C to A, see, first condition I have to check that I'm coming out, basically C to A means I'm coming out from B to A. So for G1 should be satisfied. So first thing is that G1 should be satisfied. And it will be not G4. Why? If there is a transition from G4, then C at that time can go to D. And there is also another thing, the G minus G4. That means either G4 is there, then also this action 1 will take place. If G4 is not there, G4 means the transition will take place from C to D and this action A4 will be set. So whatever it may happen, whether G4 is there or whether G4 is not there, in any case, because that is coming out from the substate to the superstate. Subcomponent C to coming out, another making a transition to A. So in any case, the transition, if G1 is there, then it will come to A. But there is one change in both the cases. When it is coming to, when G4 is on, G4 is 1. In that case, we have to consider both the actions E4 and A1. Because see, for G4, the action E4 should take place. So it will first perform the variables related to A4, or if A4 is a extended variable, then it will set the value for that. And it will also set A1 because G1 is high. But if G4 is, it is not G4, then it will only consider this action A1. Okay. Similarly, the rest are very similar. C to D also. If G1 and G4, so that is it will go to the, what to say? It will go to A4. Yeah, it will be. I think it will be not G1. Yes, it will be not G1. It will be. It will. Yes. G1 is, if G1 is on, we will always come out. It will be not G1, okay? And it is, if it is G4, it will make a transition to D. And if from D to C, it is clear that if it is not G1 and G3, then it will make a transition according to this A3. So rest are very similar, but only thing you have to understand, when D subcomponent is making, so similarly you can check for D2A. I will not repeat. But only thing you have to understand, whenever this G1 is high, the priority of G1 is so high that when it is on, when it is 1, then in spite of the fact that your G4 is also 1, but the transition will take place from C to A. And if G4 is on, then that respective actions will be taken place. And if it's not on, that action will not take place. Okay, so this is the concept of hierarchical state machine. Is it clear? I think too much for today.
Clear.
Do you have any doubt? Please go. Hello? Are you there?
Yes, ma'am. Am I
Okay.
audible?
Okay. Yes, you are audible. Tell me.
This, it's clear. That's what I was thinking.
Okay, so that is a special part because there may be some ambiguity if G1 and G4 both are high. So what will be the next possible transaction? So always that is a priority of G1. That means always the priority that you are making these priority of what I say super state transition. That is the concept. So I'm not going to I'm not starting the other models. Maybe next day we will take those things. So that's all for today. So just go through the detailed part of the cascade design, synchronous, asynchronous, and this hierarchical state machine. And next day, let me know if there is any question. Okay. Do you have any questions as of now? Just let me know. Okay. Then that's all for today. The other models I will start next day.
Thank you, ma'am.
Okay. So thank you for today. Maybe next day we will start again. Recording was actually about the books now you know, right? The 2 books I have already shared in the chat. So I think you know. So that's all. Thank you.